So let's focus on solving some example about Riemann sum. As in my previous tutorials, we were able to talk about what Riemann sum is and how we will be able to, or we can compute Riemann sum, of which we also call it approximation of rectangles. You approximate the rectangles and you add their respective areas to get the total area under the curve. So one thing that you have to know is that when you approximate these rectangles to find the area, the more accurate that you want your answer to be is when you use smaller subintervals, and hence more rectangles will have to be used. So when you use 10 intervals, the result that you get when you use 30 intervals will be more accurate, which is closer to the true value than that of the 10 intervals. When you use 30 intervals and use 50 intervals, the result that you get for the 50 intervals will be more accurate than the one that you use the 30 intervals, right? So the accuracy of the Riemann summation depends on the number of rectangles that you have to use. So now let's go straight in solving this example. So the question is, consider the graph of f of x equal to 600x minus x squared over the interval 0 to 600. A. We should approximate the area by dividing the interval into 6 sub-intervals. And B. We should approximate the area by dividing the interval into 12 sub-intervals. So first of all, whatever we need to do is to know how our graph will look like. And I know that you have done graphs of a function, how to graph this. When you take a very close look at this function, you can see that it will be a maximum function. And when I say a maximum function, the graph will be like this. And the minimum function will have a graph to be like for quadratics, right? And this is because the coefficient of the highest power, which is x squared, is having a negative coefficient. And therefore, it will be a maximum value. And then if in case here was plus, then it should have been a minimum value and it should have been like this. But in this case, it's not plus. Therefore, it's a maximum function. That's what you need to take note. But first of all, we don't know the turning point. Because the quadratic, you need to know the turning point. And how are we going to get a turning point? And we can get a turning point by basically doing something to the function. So how do we get a turning point? So in your calculus tutorials earlier on in your calculus 1, how did they tell you if you want to determine the turning point of a function? So based on that, if you are able to determine the turning point of this function, you will be able to evaluate for the value of that of the turning point of the function. That's something that I need to take note of. That's something that you need to take note of. But for now, let's keep the turning point aside because we are going to use those intervals that we are going to use to evaluate for the value of y. So that's one will help us to estimate the height of the parabola. Let me say the height here, the turning point where we are going to get. So first of all, now let's go and compute the Riemann sum based on what we learned earlier, which is this one. If you want to compute a Riemann sum, that's the area of the respective rectangles. It's fx of 1 and then change of x and so forth, right? And then the question was telling us that we should divide it into 6 for the first part. So you can draw your graph here. You can draw your graph here, but remember that it starts from 0. It's starting from 0. So if it's starting from 0, that means that the division will be up to 500. The division will be up to 500. So that's the normal line division, but the rectangles is supposed to be up to 6. So based on that, when we take the function, here it's our y, and here it's our x. So the function, it's f of x equal to 600x minus s squared. So when we take the function here and then we put 0 inside, f of x of 0 equal to 600 times 0 minus 0 squared, which is equal to 0. Therefore, here our value of y, it's what? F of x is what? 0. And then, since we are dividing the 6, let's also look at our interval first, so that we can use the interval to do our division. And for our previous tutorials, we discussed that when you want to find the interval, you do b minus a over n. And here, the number of subdivision is 6. And then I told you that the b minus the b stands for the end point and the a stands for the starting point. And then the end point is what? 600 minus the starting point is 0. And then the number of subdivision, the triangle that the rectangle that they say we should divide is what? 6, which is n. And therefore at the end of the day I'm going to get 100. So if my first point 0, it's giving me 0 over here, then my next interval division is 100. And therefore when I multiply 600 times 100 minus then 100 squared, what am I going to get from here? Which is what? 50,000. When I do that, I'm going to get something like, let me say 50,000. So 50,000, you write a 50,000 there. And then f of another one, that's the f of the next interval, it's x of 200. So f of 200, because from 0 to 100, 200 is equal to 600 dots 200 minus 200 squared. And then at the end of the day, you are supposed to get 8,000, and then you do it up to the last one, of which you are going to get f of 500, right? X of 500. X of 500. That is 100, 200, 300, 400, 500. Here, x of 500. Then at the end of the day, we are going to get 600 dot 500. Sorry. Dot 500. Dot 500 minus 500 squared, and at the end of the day, we are going to get 50,000 as well. So now you come here and then you do your division here. So let's make them straight. So now we can say that our graph is this one. Right, sorry for this one being a straight line. It's not supposed to be a straight line, instead it's supposed to, pass here. Yeah. Fortunately, yeah. So that's how it is. So this is how our graph will be like. So this is our final graph, and then it will be having a rectangle of 6, because here the rectangle figure here is 0. So 1, 2, 3, 4, 5, 6. So here is 0, 100, 200, 300, 400, 500, and 600. Right. So from 6 interval, we know that here is our rectangle, 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 and then rectangle. So 1, 2, 3, 4, 5, 6. So from here, you do the approximation as usual. So what you can do is that since you have already found this, x equal to 600 minus 0 over 6, which is equal to 100. That's our interval. We can also say that the area under the curve will be approximated as the sigma I equal to 1 to 6 of f of x1 change of x. When they say to 6, don't assume that by all means we need to bring this 600 as part of the equation, because we started at 0. If we started at 100, then it should have been 100, 200, 300, so that 600 will be included. But we started at 0, so 0 is counted as part, so the approximation will be 0 should be 1 here, this one should be 2, 3, 4, 5, 6. So a number of intervals has finished, right? But if you use a rectangle, I think you'll be clear of it. So the rectangle here, 1, 2, 3, 4, 5, 6. That one will make a little bit sense. So basically, the approximation will be equal to the sigma I equal to 1 to 6 f of x I, and then change of x. And therefore, we are going to get f of 0 multiplied by the interval, which is what, 100. Always the interval is constant, plus f of 100 multiplied by the interval 100, plus f of 200 multiplied by the interval 100, plus f of 300 multiplied by the interval 100, plus f of 400 multiplied by the interval 100, plus f of 500 multiplied by the interval 100. So this is the approximation, and then from there, when you simplify it, f of 0, we got 0, and then times 100. Okay, let me use dot so that you don't confuse my x. Times 100 plus 50,000 times 100 plus 80,000 times 100 plus 90,000 times 100 plus 80,000 times 100 plus 50,000 times 100. So this is the same thing that I was doing here to let you understand that this is what they did. They inputted a function here to get those ones over here. And from here, we are going to get a final approximation answer to be 35 million. Yeah, so this is what we got when we use a subinterval of 6. So let's look at the B. So the B, they are telling us that we should use approximate the area by dividing the subinterval into 12. So based on this one, let's quickly draw our figure here, x and y plane over here. Let me quickly draw. I want it to be straight. Let's quickly draw our x and y plane here, and then let's go here. Yeah, so now we have our y, we have our x, but first of all we need to calculate for the change in x. So the change in x equal to b minus a, always quote the formula over n. Here our n is 12, therefore we have 600 minus 0 over what? 12. This is what we are going to get, right? 600 minus 0 over 12, and we are going to get what? 50. Therefore our interval change of x is going to be what? 50. So if we start from 0, the same procedure as we did up there, up to 50 here, it should be 0. And then when we evaluate it, we are going to get the evaluation of that means we are dividing into 12, right? So 0 part is a one rectangle here. So one rectangle is here. We put another rectangle here. We put another rectangle here. And so we do it as it is. So now let's count our rectangles. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right, so currently we have 12 rectangles, and then you need to remember that this is our graphs. Supposed to pass through here. Sorry for not drawing the graph all. Yeah, so that's a curve like that, and then from there, whatever you have here, we have our 12 interval. You can just label it if you want. So now we have you can label it here from 50, 100, right? 150, 200, 250, 300, 350. I think when I turn it this way, it will help. 400, 450, 500, 550, 600, right? And then this is what I have here. So if you have been able to evaluate for the value of y using the function f of x equal to 600x minus x squared, you'll be able to just also label this part as well. So I'll leave that one to you to label it as well. So the whole approximation will be like the sigma I equal to 1 up to 12, f of what xi, change in x equal to f of 0 times the interval 50, which is constant, plus f of 50 times 50 plus f of 100 times 50 up to f of 550 times what 50. So when you calculate them, you are supposed to get a 12 rectangular approximation because the 0 is included, and then therefore in all you are going to get 0 dot, because when you put in 0 to the function, you are going to get 0, this function, and then 0 times 50, plus 27,500 times 50 up to that one, up to 27,500 times 50. So when you get this, the final answer that you are going to get is 35,750,000. So you can see that the difference here, the first one with the 6 approximation of rectangles, and then the second one with the 6 approximation of 12 approximation of rectangles have some difference, and then you can see that 35,000 minus 35 million, right? Here 0.00057. So as you can see, the difference, it's 750,000. This means that the more you divide, you increase the subinterval, the more accurate you get your value. So this is a very huge significant figure. So take note, the more you increase the rectangles, the more you get to the true value. And with time, I'll also use GeoGebra to demonstrate how you can find Riemann summation. So I'll go a little bit into technology in any time. That's I think the video will come in separately in no time, so keep watching, and then share the link to all your friends and other people as well that you know that you think they may need this kind of tutorials. Thank you, and see you in my next video.